All right. Let's deal with, well, basically transitioning from fixed point iteration to Newton's method. Okay. Now, you guys been able to watch the video Abby and Stephanie from Monday?
I watched it.
Okay.
Is this 1.4 or 1.5?
Yeah. I think it's scheduled might have had 1.4, but I did that on Monday and I'm gonna like recap it now.
1.4?
Yeah.
Why are you recapping? I'm gonna grab my laptop and I can follow along.
Okay. Yeah, because 1.4 is like one page. So. Okay. It's kind of weird. I kind of patterned this after the textbook sections, and some sections are like nothing, and then some are really long. I don't get it, but okay. So as a recap, that
Dr. Ross.
if we solve the equation f of x equals 0, using fixed point iteration, with a g, so fixed point iteration, of course, is solving x equals g of x. With this choice of g, x minus a constant lambda times f of x, and this is called, so doing this with any constant lambda is called relaxation. Okay. And if we have this assumption, f prime x is at a root is non-zero. Now in the discussion from Monday, I made a simpler assumption that it's positive, but everything would work the same way if it was negative. The point is, it's non-zero. Then the best choice of this constant lambda is 2 over little m plus big M. Okay, that's your choice of lambda, where f prime is bounded by so little m and big M are lower and upper bounds on f prime on some interval x minus x star is less than some delta, because if f prime is non-zero at the root, then it's going to be non-zero on some sufficiently small interval containing the root. So that's just by continuity. Okay. And the reason why this is the best choice of lambda is it minimizes the size of g prime on this interval. Okay. Because the smaller g prime is, it's around near the root, the faster convergence is going to be. So this leads to, now the thing is, in this case, we're choosing lambda to be some fixed constant, and we use that constant all the way through the iteration. But since this is like 1 over, you kind of think of this being like roughly 1 over f prime. So instead of letting lambda be fixed, forcing lambda to be fixed throughout the iteration, what we can do is vary the iteration. we let lambda k, it's a variable now, 1 over f prime at xk. And a reason for that is g prime of x would now be, if we take the derivative of this, 1 minus f prime of x over f prime of xk. And therefore, g prime of xk would be 0. So that's what we would prefer. We would like g prime to be 0 all the time. And what we really want is for it to be 0 at the root. So what this means is if we make sure that g prime is equal to 0 at every iteration, then our limit as k goes to infinity of the new error
It's 1 minus f of x over f prime x. Is that right? That says?
yeah, 1 minus f prime of x
Prime of x.
over f prime of xk. But then if I go ahead and set x equal xk, then all this would become 0. Okay. So then this limit, which for fixed point iteration we already know to be absolute value g prime at the root, would be 0. Because we're keeping g prime 0 at every single iteration. But from our discussion of order of convergence last time, when we have this situation, here we have our old error to the first power. So normally that's linear convergence. But if the constant, so this is our asymptotic error constant, which I was calling c the whole time, if that is 0, that is not linear convergence. What is that? What? Well, we don't know yet it's quadratic.
Maybe
We will- Superlinear, yeah. So this tells us it's at least superlinear. So when you have your old error to a first power in this definition, but the limit is 0, that tells you it's superlinear. Now, the thing is, when you show us a certain order of convergence, it's possible that it's better than that, and that will be the case. We just haven't shown that yet.
I got a question about that.
Yeah.
That one again. It's 1 minus f prime of x over f prime of xk.
Yes.
Which equals, is that g prime or double prime?
This is here.
That
Oh, that's g prime.
G prime, okay.
Yeah, sorry, I drew a line there. Yeah, so, and because all of these xk's are converging to x star, then g prime of x star is going to end up being 0 also. So we're changing the g from one iteration to the next. So that's what gets us this faster convergence. So because normally in fixed point iteration, you normally think in terms of using the same g, but now we're going to define g in terms of not just f, but f prime. So what to suggest is, because everything we do in fixed point iteration, we just say, okay, we're solving this equation x equals g of x, and we have no idea what g is. Now, I gave some pointers last time on how to pick g, but again, they're just guidelines. It'd be nice to have a more concrete iteration that's like, okay, here's the f, I want to solve f of x equals 0. What is my iteration going to be in terms of f? And now we have that. So this leads to Newton's method, which is equivalent to fixed point iteration. So now I'm getting into, well, yeah, now I'm really getting into section 1.5. Fixed point iteration with a specific choice of g. G of x is equal to x minus f of x over f prime of x. Okay. So the actual algorithm for Newton's method is you choose an initial guess, and then you have a loop where each new x is equal to this g evaluated at the old x. But I can write out what that is this time. Xk minus f of xk over f prime of xk. And then you check for convergence. So for instance, you look at xk plus 1 minus xk, less than some tolerance, for instance. So if the x's are getting so close to each other that they're practically indistinguishable, then you might as well stop. And if it converges, then xk will converge to a root of f. All right. So this is one way to see where Newton's methods come from. By using all the theory from fixed point iteration, trying to make fixed point iteration more rapidly convergent, Newton's method falls out of that. So using this relaxation idea. But there's another more intuitive way, like geometrically, to see where Newton's method comes from. So I'll do that. So a geometric derivation. So what you can do is find a root of f of x equals 0. You can instead find a root of, instead of working with f itself, work with a much simpler function. Because of all the different functions out there, what's the easiest kind of function to find a root of? More specific than that. Yeah, a linear function. Yeah. Yeah, because every line, except for like a horizontal vertical line, has a unique root. So, if we want to approximate f of x by a line, well, we can't just choose any line. What would be a sensible kind of line to choose? If f is what, if f, it could be anything. But what's a good way to approximate f by a line? What kind of line? Tangent line. Yeah. So we can find a root of a tangent line. So f of x is now approximated by, so we can pick some x naught, that'd be like our initial guess, plus f prime of x naught, that's the slope. So I'm using point slope form here. So we see where this is equal to 0. And I'm going to call the root that we're looking for, I'll call it x1. So we're going to find the x1 that makes this whole expression equal to 0. So now I can take this equation and go ahead and solve that for x1. So, do the algebra. What is x1?
Let's see.
Is it just gonna be the, do we take the function part out of it too?
Well, the only thing we put in a box.
Is it
F-
oh, it's equal to 0.
F of x.
X is not.
Negative f of x.
No, there's
0
no in the
over
provide
f prime
line.
of x 0.
You have to
You
divide
divide
by
by
both.
that negative, so
Um,
It's gonna be x naught.
It's going to be x naught minus
Minus
f of
f
x naught over f prime of x1.
Okay, that's what I said.
F prime x
backwards.
naught.
I
said
just looked over
negative
there.
that plus
Oh,
x
oh,
0.
okay, yeah, you can do. I was wondering if someone would cheat.
That's me.
Okay.
That's what I got.
Friends were talking about Math 500 this morning, actually. So yeah, because you move this to the other side, both minus, divide by that,
Yeah.
and then move the x naught over, and there. Okay, so there's your, hopefully a better approximation of a root. So let's draw this. And the thing is, I was going to drawing a bad example, but we'll see how it goes this time. Okay, so like here's x naught. So in this case, nowhere near a root. So if we draw the tangent line, try to draw that accurately. Okay, so this is a good example. And we go ahead and find a root, and that's x1. So we've gotten a lot closer in this case. And now we can just try again. So up here, do another tangent line. Kinda. And that is x2. And you can see now we're like really, really close. And we can keep doing this until we're satisfied with how close we are. So again, the same iteration pops out. Xk plus 1. So to find the root of each tangent line, we can use this same formula. So we're coming at Newton's method from two different perspectives. Using a tangent line approximation or using fixed point iteration. And when you're trying to design a numerical method, this point of view, something like this, is often useful because first you should ask yourself, for whatever kind of problem you're solving, like a root finding problem, what kind of function is easy to solve a problem with? In this case, a linear function. Okay, now, how can you use that idea for a general function? Answer, the tangent line. So this is going to be a recurring theme all semester long. Like for instance, when we get to approximate differentiation integration, for what kind of function are those problems easy to solve? Polynomials. Okay, so how do we handle general functions using the appropriate polynomial approximation? And then we go from there. So it's always good to have that perspective. Identify the easy categories of problems and then figure out how to reduce your problem to that case. Okay. So any questions about this tangent line stuff? Okay. All right.
I have a question about relaxation.
Yeah.
Previous session, we find out is quadratic convergence, but today it's super linear. Actually, it was my question.
Well, the thing is, yeah, well, like I said last time, we can't see quadratic from here.
So
Everything I did yesterday or Monday is enough to show that relaxation of this form is superlinear, which now allows for actually faster convergence to that. So I did not prove quadratic on Monday.
Okay.
Yeah, I just said it. So
Okay, but the correct one is super linear.
well, all I can say is we see from this it is at least superlinear. Because we, in this case, we saw in terms of at least superlinear, we have not ruled out quadratic. But the thing is, what we're able to do here, and like this part I didn't really cover last time, but because to prove quadratic, you have to look at this error over the previous error squared. And all of this analysis isn't really going to help us figure out what that is. So, yeah, so I mean, I'm sorry if it sounds like there's any inconsistency between Monday and today, but there's not, I promise you. Okay, it was superlinear both times, that's what was shown. I just also, because you could show it a different way that is quadratic.
So it means that it could be, it depends on,
Yeah, well, because the thing is,
it could be both, depends on the condition.
yeah, because when you show this, all that tells you, if you get this result, that is like it gives you not the actual order of convergence, it gives you a lower bound. Like for instance, suppose you show a method that's quadratic, because you get this error over this error squared goes to a constant. Well, actually, in that case, if you get a non-zero constant, then it really is quadratic. But when the constant is 0, that means that a faster order of convergence is still possible. So what we know here is we know the order of convergence is greater than 1. So this number r that I use to refer to order of convergence. But it doesn't tell us that it's less than 2.
So there is a range for it.
Yeah.
Okay.
Yeah, because the thing is, if a method is better than linear, so r is greater than 1, but you also know that it turns out to be quadratic, then you might as well call it quadratic, just because it's more informative as to what the actual speed of convergence is. But yeah, you can really, it's customary to call it superlinear when r is strictly between 1 and 2, when you know that. But technically, like just English usage, superlinear really means anything greater than 1. Yes, part of it's like just what the terms mean. But yeah, so but the point is, this analysis either Monday or today did not show anything about it being quadratic. That's coming. Okay. Are we good? Or
Yeah, kind of.
well, I'll check with you at the end. Okay. All right. Okay. I'm wondering why the University Police Department is telling us to be cautious. What?
There was some robberies.
Armed robberies on campus.
Yeah, like Sonic.
Shut up.
Sonic,
Westport.
Sonic Drummond and Hogan's Express on Westport Street.
oh, that's close to my house.
Oh, jeez.
That's how I have a shop.
Oh, boy.
That's why I have a gun. Yeah, that's why I got a pistol last week.
I was back then, but I don't want to get shot.
Okay.
That's a state of Mississippi rule.
Now, so here's an example involving Newton's method. So I can use a very simple function, but still something of interest. Okay, so x squared minus 2. So, and we know what the root is. It's going to be plus or minus the square root of 2. So that f prime is just going to be 2x. So now our Newton's iteration is xk plus 1 equals xk minus f of xk over f prime of xk. So now what we can do is simplify this, because if I break this into 2 fractions and simplify as much as I can, I'm going to get xk over 2 plus 1 over xk, just from simplifying all that. So now I have an iteration that will compute the square root of 2 for me. Just using simple operations, just using addition and division. So I'm going to choose x naught equal 1, so that's my initial guess. So now if I go ahead and compute x1, so we get 1/2 plus 1 over 1, so I get 1.5. Does anyone know the first few digits of the square root of 2?
1.404.
Oh, close, 414, yeah. 1.414, 2135, etc. All right, so then you do 1.5 over 2 plus 1 over 1.5, which turns out to be like 17 over 12. So it's 1.416 repeating. So okay, we got those first decimal places already after just a couple iterations. And then we do another. So x2 over 2 plus 1 over x2. And we get 1.41421. So these 5 decimal places are correct. In fact, if we do a couple more, like just up to x5 would give us, we'll get up to 8 decimal places on the very next iteration. So what ends up happening, if you look at the error, it's like the number of correct decimal places is roughly doubling from one iteration to the next. So if I went one step further, I'd have full precision, because in typical computers with double precision floating point arithmetic, about 15 or 16 decimal places is the most that you can expect. And after like 5 iterations or so, we get that. So this is something you can try on your calculator and very quickly get any square root. So of course you can adapt this to any square root. I should point out that if x naught is positive, the root that it converges to is positive square root, and if x naught is negative, then it converges to the negative square root. Okay. All right. So, in fact, I wonder if this is how a calculator actually computes square roots, because it's just using these very simple operations, with just about any initial guess, you could you know how it's going to take very few iterations.
I thought Newton's was the one that had to be close to the x naught.
Generally, yes. And actually, my next example is going to illustrate how it can go awry. Yeah, because you can only be confident. So there's actually a theorem in the notes that it's a very useless theorem, actually, which is why I didn't even bother running it down. That Newton's method is guaranteed to converge if the initial guess is sufficiently close to the root, and if it's then if it's twice continuously differentiable, and actually I think I have a typo in the notes. I better check this because I have f being 0 to root, of course, and f prime being 0, but it really should be non-zero. Okay, because Newton's method is going to have a problem if f prime is 0 at the root. It doesn't fail though. It's actually because you're not really evaluating that derivative at the exact root. It's something that's getting really close to it. So what happens in that case is it slows it down a lot. Okay, so but the thing is, this theorem, it says that the Newtons will converge if you're close enough to the root, but it gives no idea of like how close you have to be. Like I said, it's a pretty useful theorem. It's not like a fixed point theory where there's some definitive conditions where you can guarantee convergence on an interval. Unfortunately, Newton's method does not have that. Okay. So here is my favorite Newton's method example that illustrates how it can work so well and also fail so catastrophically. So in this example, our function of choice is some constant a minus 1 over x. So what's the root?
Is it a?
A
A
x
minus
is not A.
No. I'm asking if fx is equal to a.
No, you moved it.
Oh, what is that thing there?
This is some constant A.
Oh, okay.
Okay.
She can't read it.
Oh, okay. Okay, well, so what's the root?
1 over A?
Yes.
Because then it's A and it's A?
Yeah. Okay. So this is a function where we can find a root. The root is the reciprocal of whatever A is. Now, it seems like a silly example until we actually try Newton's method on it. So, because what is f prime of x?
1 over x squared.
Yeah, 1 over x squared. Okay, so now our Newton iteration, xk minus f of xk, so it'd be a minus 1 over xk, over f prime. But now, suppose I go about simplifying this, because I can multiply top and bottom by xk squared.
Is it negative? Like f prime of x negative? Right?
No, because I have a minus here.
Oh, okay. Oh, my bad. Okay.
Okay. I'm glad you got that worked out. So then I have, my denominator becomes 1, and then I have axk minus, plus xk. Oh wait, this should be xk squared. Okay. All right, and now I can simplify this once and for all. So I have 2xk minus axk squared. This is my Newton step. Okay, now, seems simple enough, but the simplicity is not the most interesting thing about this. There's no divisions. We have multiplication, we have subtraction, but this allows us to compute the reciprocal of a number without performing any division. And the reason why this is significant is back in the 60s, one computer made by IBM actually used this to implement division in hardware. So they have an addition circuit, a subtraction circuit, and a multiplication circuit. There was no division circuit. They just used this. Actually, one faculty member here in computing, who's since retired, Dr. Seyfarth, he, one time over lunch at McDonald's, he talked about how this was actually the best way to perform division. And I thought, what an interesting claim, because as you can see in my example, you need a good initial guess for this to work. And then I thought about it, and it's like, oh, that can be done. And actually gave it as a bonus problem in like 460, 560. So I could throw it out as a bonus problem for you guys too. I just need to write it up. But let's go ahead and try this iteration on some examples, and let's see what happens. And see what's happening geometrically is quite illuminating. So I'll let a equal 12. So that's my favorite number. So the root is 1 over 12, so that's 0.083 repeating. So I'm going to choose initial guess of 0.1, and let's see what happens. So I have x1 is twice that minus 12 times that initial guess squared, and so you work it out in your calculator, and you get 0.08. Okay, so that's a good start. Already got 2 decimal places. And then x2. Oh, dang it. Okay, my notes are off, but I'll fix that later. Okay, so we get 0.0832. Okay, so we picked up another decimal place. Okay, I'm going to write down how many decimal places we have correct. So we have 2 here, 3 here, And then x3, we just repeat this process. We get 0.0833312. So that is 5 decimal places. So we're making good progress. And if I do another 0, 8, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it deviates from there. So we have 11 decimal places correct. So this is what I mentioned earlier. The number of correct decimal places approximately doubles from one iteration to the next. There's no point, maybe we could do one more, and then we'd have it do like as many decimal places as we can hope for on a typical computer. So convergence is very fast. Everything's hunky-dory. Okay. Now, let's try same problem, same value of A, 12, but my initial guess would be 1. So a lot further away from the true root. So x1 would be 2 times 1 minus 12 times 1 squared, and we get minus 10. That's a little discouraging. Let's do another. Maybe we can make a miracle comeback. That's 12 times minus 10 squared, and we get minus 1,220. So look a little bleak. And if we did that one more time, it'd be like minus 17,863,240, and it's probably a good idea to give up. So this is a problem. So I'd like that idea as to why this happened, and we can get that idea by looking at the graph of f. Because all I'm doing is I'm taking the function 1 over x, and first I reflect it across the x-axis, like by negating it, and then I shift the graph up by a, and that gives me the final graph. Okay. Okay. Now, if I draw this graph carefully, all right, so I actually want my x-axis down here. Oh, okay. Unfortunately, my picture in my notes is, I did it first for a different value of a equal 8. So I'll need to change that in notes. I keep forgetting to. All right, so here we have the true root, x star equal to 112. And then way up here we have where the horizontal asymptote is. The horizontal asymptote will be at y equals 12. So the graph will go, here's your root, and then it behaves something like that. And then you have the other part of the graph behaving like that, going all the way out to minus infinity. So, in the first case, I chose my x naught to be right around here. So I do a tangent line, and so a tangent line passes through here, and then so everything works out pretty well. But if I choose my initial guess much further away, like over here, so x naught equal 1, what's going to happen to the tangent line? Where's it going to intersect? Yeah. So if we go ahead and draw that, yeah, it's way out here, and then we're lost. We go up here, draw another tangent line, and it's going to send us into Siberia. So that's what we want to avoid. So we want to make sure that if since our root, our root is positive, our initial guess is positive, we want all our iterates to stay positive. So to ensure convergence, and this is like a necessary condition. It turns out to be sufficient, but that takes more time to prove. But I can definitely show you it's necessary. We need x1 to be positive. Well, so that means we need, but x1 is equal to 2x0 minus ax0 squared must be positive. And if you solve that inequality for x0, you get this condition, that x0 must be less than 2 over a. So the thing that's unfortunate is you might think, oh, well, this is useless because in order to converge to 1 over a, your x0 needs to be so close to the root that it's almost like you have to know something about the root to get the initial guess for a root. And that's why when Dr. Stefan made a comment about how this is the best way to do division, I was like, are you high? But then when I thought about it in terms of floating point arithmetic and how numbers are represented by on computers, actually makes a whole lot of sense. That because the way we represent computers, you have some information about the magnitude, like its exponent in base 2, and you know some of it's not decimal digits but binary digits. So from that information, you can actually come up with an initial guess that can guarantee to satisfy this. So on a computer, it actually is practical to use this. Now, I guess folks at IBM decided not to continue with this. They eventually implemented their own division circuits. They don't use Newton's method anymore, but they gave it a shot. Sometimes, we got to try all these things. Like, for instance, computers all work on base 2. Like the Russians tried base 3 one time. I'm not sure how it would work because binary makes sense. Like 0 equals off and 1 equals on. So what's this, other state? And it makes you wonder what they're doing over there. Well, I always joke that all mathematical problems have already been solved. They just haven't been translated from Russian into English yet. So, okay. So this shows that in certain cases, you have to be very careful. Whereas with that previous example of a square root iteration, it turns out for that one, any initial guess would have worked, no matter how far away it is. It might take a little longer, but because the function so nicely behaves, this nice parabola. So if you have a function that behaves very nicely like that, like for instance, if it has constant concavity, like always concave up or always concave down, you can actually prove, and I do have a theorem about this in the notes, that you can guarantee convergence over like a really large interval. So it all just depends. Okay. Let's see how much further I need to go. Okay. And how much time do I have? Okay, I think we're good.
So, like, a well-behaved function is more lenient on your initial guess.
Yes.
Like you can.
It's when things are more oscillatory, or when you have asymptotes like this,
Right.
then you might be in trouble. Okay. All right. So, at this point, based on this previous discussion with relaxation, we know that this choice of fixed point iteration that gives us Newton's method, we know it's super linear. But now we can, there's actually 2 ways I can show you that it converges quadratically. But I'm going to do the Taylor expansion one because, yes, it's harder, but it's more fun. Besides, Taylor expansion is such a fundamental part of numerical analysis that you should all be exposed to it anyway. All right. Actually, what else do I have after I do that? I'm definitely not doing that proof. Okay. And that I already did. Oh, that's a good example. Okay. Okay, so we're going to assume f is twice continuously differentiable near x star, near the root, and f prime of x star must not be 0. And I mentioned like the very first day how when the derivative is 0 or nearly 0 to root, how that causes problems for numerical methods. And I will have one last example about that. So recall this definition I gave for error analysis. EK, the error after k iterations, is defined to be your kth iterate minus the exact solution. Okay, so now what I want to do is relate the new error to the old error. So I'm going to recall what happened with that with fixed point iteration. For x equals g of x, you get ek plus 1 is equal to g prime at some unknown point times ek. So the ratio of errors turned out to be like g prime of x star. This is so what happens is the ratio of errors converges to absolute value of g prime at x star if it is non-zero. Okay. So in that case, it was linear convergence. And this was your C, which I call the asymptotic error constant. And because the power of EK is 1 in this case, that's linear convergence. Okay. But what we also saw was that if G prime at x at the root does equal 0, then we have EK plus 1 over EK squared converges to 1/2 G double prime at x star. So this is quadratic convergence, and this is your C, assuming this is non-zero, and so forth. So however many derivatives of G are equal to 0 tells you your order of convergence. Okay. Now, that's fixed point iteration though. What about Newton's method? So a similar analysis, but it's harder than what we did for fixed point iteration. So the error after k plus 1 iterations is xk plus 1 minus x star. And then I can replace xk plus 1 with its definition from Newton's method. But now I have xk minus x star. Well, that's ek. So grouping these first and last terms together, and I still have this. Okay. All right. But now what I need to do is work with this to see what is the real relationship between ek plus 1 and ek. So what I'm going to do is I'm going to do a Taylor expansion around xk. So I'm going to use that as the center of my expansion. So when I do that, what I get is f of xk is equal to f of x star minus f prime of xk, x star minus xk. And then I'm going to have one more term, minus 1/2 f double prime at some unknown point, which I'll call xk, xk minus x star squared, all over f prime of xk. Now, normally for these things, you tailor expand around x star. It seems strange to expand it around xk, which is actually why I have minuses instead of pluses. But the reason for that is I have this f prime of xk down here. I want to be able to get some cancellation. Now, first of all, f of x star is equal to what? What is x star? Therefore, f of x star is 0. So that's gone. X star minus xk is equal to minus ek. Just by definition of the error. And this, therefore, is ek squared. So what's going to happen is, in this term, the f primes are going to cancel. And I have minus, minus, minus ek. So what's going to happen is a ton of cancellation. So this ek is this term. I can lump that in there. That's ek. Because the f primes cancel, these minuses cancel, and I have ek minus ek. So in fact, that goes away, and that goes away. Everything goes away, except this last term, which is the minuses become a plus. So I have f double prime of xek, ek squared over 2 f prime at xk. So what we find is, well, okay, I know I glossed over the algebra. It's all in gory detail in the notes. But you guys are algebra masters, right? Well, half you are teaching it right now. So you better be. Yeah. But yeah, if you expanded all this out and did simplification, you would see, bam, it goes away. I'm trying to save time. So, okay. So because each error depends on a previous error squared, that's how we get quadratic convergence. So we can see from this that the limit as k goes to infinity of ek plus 1 over ek squared, absolute value, is f double prime at x star, because this is an unknown point between xk and x star, but xk is converging to x star. So the numerator will converge to f double prime at x star over 2 f prime at x star, which is why I had to assume that it's non-zero. So this is your asymptotic error constant in that case. So so in fact, if you go back to like the previous examples involving like computing the square root of 2 or the divisionless division, you can go back to this and figure out from that f of x what the asymptotic error constant is. But that is less important for quadratic convergence than for linear, because linear convergence, and you want the error constant to be asymptotic error constant, that c, to be as small as possible for rapid convergence. This is going to converge rapidly anyway. And yeah, you prefer that c is not huge, but. Is there any questions about this?
Is that the 2 on the ek? Is that for the r or for the
this?
other? Yes.
Yeah, that is r.
So that means quadratic, right?
Yes.
Okay.
Yeah, when you have the new error is equal to something times the old error squared, that's quadratic convergence. Whereas here, we had new error is something times old error to the first power, that's linear convergence. Any question? Now, that's a more painful proof of quadratic convergence. Here's a simpler one. Because remember, Newton's iteration is a form of fixed point iteration. So if we look at our G for Newton's method, it's x minus f of x over f prime of x. So what you can do is you can go ahead and, let's go ahead and compute G prime. G prime is 1 minus, and unfortunately you gotta use the quotient rule for this. So it's f prime squared minus f double prime all over f prime squared. And once again, you can simplify this a ton because you have f prime squared over f prime squared, which gives you 1. So there's a lot of cancellation again. And what you get is f prime, f double prime over f prime squared. Now, what if I plug the root into that? What am I going to get?
0.
Yeah, because I have f of, yeah, because x star is a root of f. So you get g prime of x star is 0. So we get quadratic convergence. Or I should say at least quadratic. In order to be sure, you have to look at g double prime from here, but generally that's going to be non-zero. Okay. So that's one way, yeah, because if you can come up with a fixed point iteration, x equals g of x, where you can be sure that g prime is 0 at the root, that's quadratic convergence. Okay. I don't need these pages anymore. But all of this was contingent on f prime of x star being 0. And so now it's informative to see what if that doesn't happen. How does Newton's method behave in that case? Because on the one hand you think, okay, if f prime is 0 at the root, Newton's method divides by f prime, so you think you're setting yourself up to divide by 0. But like I said, you're not ever evaluating f and f prime at the exact root, just an approximation. So what really happens in that case? Let's find out. So I'm going to make a function where this kind of thing happens. So my function is x minus 1 squared e to the x. So what we find here is because of the x minus 1 squared, we have a double root of 1. So what that means is f of 1 and f prime of 1 is 0. Because if you were to differentiate this, you got to use a product rule, but every term in your product rule would have at least one factor of x minus 1. So it's going to be a root of that. So what we can do is, let's do the same kind of convergence analysis as before, except now we can fill in what f is. So ek plus 1 is equal to xk plus 1 minus x star. But we know what that is, it's 1. So we'll go ahead and fill that in. So that would be xk minus f of xk over f prime of xk minus 1. And then if we go ahead and fill in what the function is, so I have xk minus 1 squared e to the xk all over the derivative, and for that you got to use a product rule. So it's a little bit tedious. one nice thing is the exponentials all cancel. So what ends up happening is, so after you get rid of the exponentials, also xk minus 1 is equal to ek. And xk minus 1 is equal to ek. So I have a bunch of ek's. Ek minus ek squared over 2ek plus ek squared. Okay. Because ek is equal to xk minus 1. It's the error after k iterations. So I can factor an ek out of all of this. And I get 1 minus ek over 2 plus, oh, okay, actually 1 minus 1 over k times ek. So now I have a new error is equal to something times the old error, but to the first power. So right off the bat, that's linear convergence. And in fact, since ek is going to 0, it's still going to converge, but then this fraction becomes like 1 minus a half. So we have linear convergence. And your asymptotic error constant, C, is equal to 1/2. So you lose that quadratic convergence. Also, the ratio of errors, so the error is roughly being cut in half each time. And in fact, I don't have it in the notes, I proved it later for my textbook, that when you have a function that has a double root and you try Newton's method, this always happens. That you get linear convergence and the asymptotic error constant. You can show this is always equal to 1/2. So Newton's method will still work. It's just really slow. So instead of needing like 5 iterations or so to converge to full precision, it may take like on the order of 50. So it's pretty bad. Now you have some options. So like one way to work around this is instead of applying Newton's method directly to f, you define this new function, which is f over f prime. Because what happens is if x star is a multiple root of f, it's also a root of f prime with multiplicity 1 less. So if you cause those factors to cancel out, then so x star is a simple root of psi. So it's not a multiple root. Therefore, you can restore quadratic convergence. Can anyone think of what would be a downside of doing this? Because keep in mind, if you're going to apply Newton's method to psi of x, you need psi and its derivative. So what happens if you take a derivative of f? What else are you going to need from f? You need the second derivative. Yeah. So, but so that occurs an extra cost. So that's one problem with Newton's method. There's more work per iteration because you have to evaluate f each time and its derivative each time. And now, in this case, you'd also throw in a second derivative. So there's more work per iteration. So yeah, you may be doing far fewer iterations. So if each one's going to be more expensive, what if the derivative or second derivative are really, really complicated? Sometimes that happens. And then you might be having second thoughts. But yeah, there's other options that we'll have too. Because 2 more methods Dr. Chen will be covering when he substitutes for me on Wednesday. because I'll be gone next week, is secant method and bisection. And I'm pretty sure that's the only class I'll miss this semester. Okay. Is there any questions about this double root case?
Why did you get C plus 1/2?
Oh, because since EK is the error, that's going to 0.
Okay.
And so this
What about-
constant converges to a half. Yeah. Okay. At least it's still converging. Now, so I mentioned earlier that there are certain cases where Newton's method is very forgiving on what your initial guess is. So I'll show you one such situation that I think will be out of time. Okay. So I need to define an interval starting at the root and then extending past that point by delta. Now normally when we use letters like epsilon and delta, it's assumed that they're small. But here I'm not going to assume delta is small. In fact, delta could be as large as you like. So I'm going to assume that on this interval, I delta, we have f is increasing, so f prime is positive, and it's concave up. So f double prime is positive. So it's a situation where here's your x-axis with the root, and past that point, the function behaves like this. And if you choose your initial guess, and the function behaves like this on as large an interval as you want. So you can imagine that if you pick some initial guess way out here, you can't see how the tangent line is going to behave because when a function is concave up, the graph is above the tangent line. The tangent line is going to be down here, which will automatically cause your new iterate to be closer. And that behavior is just going to continue. So you can kind of see, like, geometrically, that Newton's method is going to work well in this case, even if x naught is like way out here, as long as you have that nature of increasing and concave up. But now what I'm going to do to wrap up here is prove that. Okay. Now, if you look at our Newton step, okay. Well, first of all, by our assumption, the denominator is positive. Also, if your function is 0 here, and then past that point is increasing and concave up, well, actually just increasing alone will do it. The function's going to be positive. So everything here in this fraction is positive. So you're subtracting something off from xk. So that tells you that your new iterate is guaranteed to be less than your previous one. And that's what we see here. Your initial guess is way out here, and then x1 is less, x2 is less. You're decreasing towards the root. All right. But now, let's look at the error. So xk plus 1 minus x star, we know from a previous analysis, it's f double prime at some unknown point between xk and the root over f prime at xk times ek squared. But the thing is, everything in this expression is positive. So that tells you that xk plus 1 is greater than the root. So each new iterate is sandwiched between the previous iterate and the root. Because you might think, oh, okay, I'm drawing this tangent line. You think, what if it sends you way over here? I'm just showing you that can't happen because of this, because of these assumptions on the derivative. So it's always going to work like this. We keep getting closer and closer, decreasing towards the root. Okay. So that tells us that this sequence, xk, and I hate to bring back any psychological scars from real analysis, but is a sequence that is monotonic. Does that ring a bell? And bounded on both sides. When you have a monotonic bounded sequence, what happens? Yes, the sequence converges. So that's to converge to something. Now, how can we be sure that whatever it converges to really is the root? So I'm going to call this limit x sub star. So x superscript star is the root. X sub star is the limit of the sequence. We'd like to be sure that they're the same, but we need to make sure. Okay. But the thing is, if this sequence is to converge, xk plus 1 and xk are approaching the same thing. Therefore, this difference has to go to 0. The only way that can happen is if x sub star is also a root. But here's the thing. You might think, well, what if it's a different root? Why is that impossible? Because this is going to converge to something. So like x sub star, you might think, oh, this is somewhere over here. Why is that ruled out?
Say that one more time.
Is it because it's constantly increasing?
Yes.
You can't have another-
Yeah, because suppose the limit's over here and it's a root. But because of these assumptions, starting from this root, the function has to increase. It has to be positive. Yeah, because f of x has to be positive for x greater than, well, for any x between x star and x star plus delta. So anywhere in this interval. So the only way this can happen is x sub star equals x sup star. I know. So that means that Newton's method really does converge to the root. And we're done. Yeah, thank God, right? So, and you can also show that it's quadratic convergence. And there are other situations similar to this. Like if you know that, if you have constant concavity, up or down, and if you know it's always increasing or always decreasing, so you have one of those 4 situations, any of those combinations, you can do a proof like this and have it apply.
Happy birthday, by the way.
Oh, happy birthday!
Oh,
Wait, do you
how
have?
about
Oh, okay.
No, but my Facebook
Yeah.
told me this morning. So
We
Facebook
should
popped up.